So in this problem, we're looking to find the length of a curve that comes from the intersection of a cylinder and a plane. Now, if we scroll back up and we take a look at our arc length formula, remember that this requires us to know how to parameterize that curve. So we're looking for some vector function r of t. So we have to figure out what that is first. And then we'll have to figure out what our time values are that we're going to integrate between. And that's how we'll solve the problem. So I'm going to scroll down here. Now, this cylinder is going to create an elliptical cylinder, and I'll write out the equation there in a moment. But I've gone ahead and I've already sketched out the elliptic cylinder, and then this equation is an equation of a plane. I found the intercepts of that plane with each of the axes by setting, if I want the z-intercept, I set x and y equal to 0. That tells me it intercepts at 2. Basically, you have this slanted plane that is coming in and slicing into your elliptic cylinder, and so this basically is going to create a diagonal slice that's going to look elliptical in nature as the curve. So that is my curve of intersection, the purple line there, purple circle. And that's what I want to find the length of. So what I need to figure out is what is the parametric equation, what is the vector function associated with this curve? And then what are the t values for that parametrization that would allow me to traverse the curve exactly one time? If you want the curve of intersection, you want to make sure that you're going all the way around and that you're not accidentally continuing to go around, because then your length would not be correct. So to figure out the parametrization, we're going to need to work with thinking about what x should be in terms of t, what should y be in terms of t, and what z should be in terms of t. And we should have some intuition about how to get started, because 4x squared plus y squared equals 4, we've seen something that looks similar to this in a parametrization when we were doing curve sketching in section 13.1. So if I were to write this equation of an ellipse in standard form, so it is an elliptic cylinder because there's no z and it's a 3D shape, but thinking of it 2D in terms of x and y, it's an ellipse. And I would divide the 4 across both sides so that it's in standard form. Now, we know that if we're parametrizing a circle where the coefficients on x and y are the same, then we just use x equals r cosine t and y equals r sine t. But we're going to have, instead of having the same coefficients on sine and cosine, we will have different coefficients because the x and the y directions are stretched along different axes because of the differing coefficients associated. So what we're going to do first is we want to leverage our sine squared plus cosine squared equals 1 formula. And to do that, we're going to instead rewrite this equation as, you can think of the y squared over 4 term as being y over 2 squared, which is equal to 1. And so if we take this term and think of it as cosine squared of t, then this term here should be sine squared of t. And that tells me that I don't want y to just straight up be equal to sine t. I want y over 2 to be equal to sine t. So this would say x equals cosine t, y over 2 equals sine t. So if I want to start writing my vector equation, I now have part of the parametrization. I have that x is cosine t, and that y will be 2 times sine t, just solving that bottom equation for y. But then I have to figure out what z is. Now, z is unrestricted by this ellipse, which means I'm not going to figure out what z should be from the equation of the ellipse. Instead, I'm going to come over and I'm going to think about the equation of a plane. because I know x and y are determined. They are set along that elliptic cylinder. But notice that the plane, once I know what x and y are, z is determined as an equation of those. So if I were to take and rearrange this equation and solve for z, I would get z equals 2 minus x minus y. And if I have that, I know what my cosine, what my x and y equations are in terms of t. So now I can just sub in cosine t for x and 2 sine t for y, and that will give me what the z coordinate should be for this curve of intersection. Oops, that should be minus 2 sine t. So those are my parametric equations, which tells me that the vector function associated with this curve of intersection is the vector function cosine t, 2 sine t, 2 minus cosine t, minus sine t. So now I am ready to use my arc length formula if I can figure out what t needs to range between in order to traverse the curve exactly one time. And one way you can think about that is, what are all the t values I need in order to go around the equation of ellipse a full turn? And that just corresponds to making sure that I have t ranges over a full period, because it's determined by sine and cosine. So what we can note here is that the curve is an ellipse that we found, slanted in space because of the plane. And if I use 0 less than or equal to t less than or equal to 2 pi, that traces the curve once. And so if I want to set up my arc length formula, it's then going to be L equals the integral from 0 to 2 pi of the magnitude of my derivative of my position that I have set up, so r prime of t. This again is speed. So I'm going to go ahead and figure out what r prime of t is at the same time that I substitute in for its magnitude. We know that when we are computing this quantity, it's going to be whatever the x component of r prime is squared plus the y component squared plus the z component squared. And so I will do that all sort of at once. You can certainly write out r prime of t separately. It's going to be, so the derivative of the x component, because x is cosine t, is going to be negative sine t. But then I know to compute the magnitude, I'm going to square the x component, and then takes the derivative of 2 sine t, which is our y component, and you get 2 cosine t, and that's squared, plus the derivative of the z component, which is sine t minus cosine t, quantity squared. And that's my arc length formula that I was looking to find. And notice this problem is set up only, so I don't need to evaluate this integral.